Hey, welcome to Math Studies. This is an exciting subject because it's what we would call a utility math subject, where you are going to be able to take some fundamental concepts in mathematics and actually utilise them or apply them in a practical sense. For these presentations, I'm going to be using screen clippings from Hayes and Harris publications, Math Studies, 2nd edition, so it'll be good to have that or the disc associated with that handy by there so you can refer to that. What have I been doing here? Well, let's have a look. It looks like a bit of a mess to me, but we are headed, see this one up here, this little function. This is the usual way in which we refer to functions mathematically in x and y terms. Very useful for using technology with it as well. But where we're headed is to this sort of function, where we want to refer to the variable in terms of that actual quantity which is varying within the practical problem, like here, time maybe, and g referring to a particular property of the system or parameter of the system. Whereas back here in y and x land, y and x could be anything. It's just talking about the relationship or the function connecting the variable. Okay, so what about this subject? Well, we could be looking at cylinders like this, wanting to say, well, if this is a storage tank, can we maximise or minimise the surface area? Or, as you would have seen in your Year 10 and Year 11 work, building a fence against an existing brick wall, how do you make the maximum area, all that sort of stuff. But this year it's going to get much more exciting with Math Studies, so because we're going to be looking at rather more complicated applications of mathematics. This one down here is what's called a surge function, because it describes the surge that you're likely to get, for example, in current when you have a power supply turned off and then you turn it on again. Surge in voltage probably would be better said. So with time you get a surge. Unfortunately, the book here has used Y. Maybe you should be using V for voltage, not mix up the ideas here. In a practical situation, we try to use the variable names there that relate to the practical situation. Over here is an interesting function. We do it in Math Studies much later on. It's to do with population growth. If you do biology, you might have referred to this as the S-curve, the curve which flattens off because of limiting resources when a population is growing. So maybe here this would be better said, should have been P up there, shouldn't it? I think so. So the population growing with time. So we're interested more, not in just y and x land, but saying, hey, how can we use those algebraic relationships to actually apply them to a practical situation? There's going to be some exciting practical situations coming up in this first chapter, which is chapter 2 of Hayes and Harris. We're going to only be looking at these that we've seen before up the top there. And later on, as we get more skilled, and particularly with technology as well, we'll come down and look at the surge function, the S-curve. This is called actually the logistic function, because logistically it's more applicable than the straight exponential. This is a logistic function for population growth. But so there's some excitement coming up. In this part 1, what we want to do is really just hone up our skills with functions and stuff. You will have also already seen this, but let's have a look at some fundamental definitions and just some quite basic examples now of working with functions. And in this first part, unfortunately, we're only going to be honing up our skills in y and x land like this up here. We won't be applying them in a practical sense in this first little section. But later in this chapter, we certainly will, and we'll be doing some exciting stuff. So come down here now, and let's have a look at Hayes and Harris' definition of functions. A function is a special relationship between two quantities. And we don't push this a lot in the usual courses now, but the set of x values that are allowable in a function are called the domain, the set of values or the domain on which the function operates, and the values the function produces are called the range. So the idea of a function, if you put in a domain value, to each of those domain values you'll only produce one range value. So the definition of a function, and this is very, very important if you're looking at applying it in the real world, you've got to say, well, over what x values or variable values, independent variable values, will the domain or will the function apply and have a domain, and then what sort of values will the function produce, and what is the rule? Let's do just a quickie here now. Let's go and say, well, let's say we've got y equals x squared, or something like that. Want a better graph? Use technology, mate. Okay, so this is y equals x squared. And so what is the domain? Is there any restriction on the values you can pump in to that independent variable x? No, you can put any values in along the x-axis. It exists all along here and in both directions. So the domain would be equal to x is a member of R, any real number. And in this course we're only going to be dealing with real numbers in our domains because it is a practical course. The range here, what is the range? Well, you can see when you square a number, it only exists up there in the top part there, quadrant 1 and 2 if you like, or all above the x-axis. So the range is y is greater than or equal to 0. You don't get any negative, so we could shade this. That's often done commonly to show that you can't reach the values down there. So that's the idea. Just getting familiar with what functions can do, what values you can pump into them, what domain values, and what values come out. So let's go down a little bit more here and have a look at their first example here. Find the domain of the function y equals f of x, where f of x equals the root of x squared, take 2x. Well, what do we want to do? We want to say, well, what sort of values can the function operate on? So when you put x's in here, are there any restrictions on what values you can find the square root of? Because you see what the function is doing. It's squaring the variable, then it's taking away 2 times the variable, then it's taking the square root of it. Are there any values for x for which this doesn't work? Well, obviously you can't find the square root of a negative, so the thing that you're having the square root of must be greater than or equal to 0. Naught's okay. The square root of 0 is 0. So you're trying to find where x squared take 2x is going to be greater than or equal to 0. So not a bad trick is to factorise it and to find out when x by x take 2 actually equals 0. By null factor law, that's when x is 0 or x is 2. So if we make a little number line here, going along the x-axis if you like, there's x is 0 and there's x is 2. You could substitute in a value on this side, neg 1, sub that into x squared take 2x, and you find you get a positive answer. Then sub in 1 from this region, and you find you've got a negative answer. Sub in 3 from here, get a positive. So it's easy to track the behaviour of this little dude here. When is it going to be positive and when is it going to be negative? So where is it allowable? Where is it positive? Well, only from here up. Oops, from there up. We will include the value 2 because you can have x squared take 2x equal to 0. You can find the square root of 0. So you can find that here. And then the other value, the other region is from 0 down. You can find the square root of those values. So the domain, or the set of values that you can pump into this function, is the set of numbers x is less than or equal to 0, or x is greater than or equal to 2. So we're just getting our head around how these functions work, and just checking that we can use them sensibly in a practical situation later on. Alright, so come down now and let's have a look at another example. We'll do some exercises in a minute. So here's another function. This time we're not interested in the domain, we're interested in finding the value the function takes at particular x values. Could you please notice this notation? We could call the function y equals x squared plus 2x plus 3. That's really a formula for the function. If we wanted to find its value at x equals neg 1, that's what this is saying. Find the value at x equals neg 1. The f notation, which is technically different as well anyway, is a little bit neater. It's saying into the f function substitute the value neg 1, because you can see when we write, instead of y equals, we write f of x equals. It's saying the function is operating on x and producing this function value. So f of neg 1 is saying in the x hole in the function you will put neg 1. So then you go and do it. Neg 1 in place of x everywhere it occurs in the formula. And of course what we're going to be interested in is other symbols for the independent variable, not just x, because it might mean something. Like it could be u representing some other variable of the system. And so f of u, we will be sticking u everywhere we see x in the function. Or we might want to put root x into the function and have the function square it, 2 times it, add 3. So you would have seen some of this in your year 10 and 11 work. So the idea, of course, is the notation with functions is showing you the replacement value for that independent variable x everywhere it occurs in the function. I think that's probably enough just warm up now. One thing to note as we go through this course, it is technology based as well. It's not huge on algebra this course, so that will be happy news for a lot of people. We're not going to be doing a lot of this algebra, but technology is important. Technology is crucial, so technology to assist at all times. So if you're not sure of the domain of a function, well, you could draw the graph with your graphics display calculator and see what the domain was. You know, something like y equals x cubed. Something like that. If you want to investigate that function, have a look on the graphics display calculator and see which x's you can put in. Well, here x is a member of R, isn't it? You can see the graph of this function keeps going up this way for larger and larger x, and back this way as well. So technology is of assistance. Now, if you're not sure of that at this stage, back at the Huddy Maths SACE wiki on that home page, there's a link to another wiki where the fundamentals of the calculator are explained up till about the end of year 10. So you could go back to the wiki there and have a look at the fundamentals for each icon or each function of the Casio 9860 Plus graphics display calculator. For the moment, I want you to practice some of these things. It will take you just a little while, half a dozen questions now, to get you back into the idea. So we'll go down and have a look at those. These are from Hayes and Harris again. So just have a look at the page of problems. There are 6 problems there. The last 2, they have suggested you don't try to describe the function's domain and that sort of thing by yourself. Graph it. Have a look at where the function exists, what sort of x's it can operate on, and so on. Now, when you're doing these problems, you might like to rewind the presentation. Just what is the definition of the domain of a function? What x values can you stick in to these particular functions? Remembering that you cannot divide by 0 here. So that might restrict the numbers you can put in place of x there and here and so on. So think through those. If you get stuck, technology will help. Okay, given that the function here, this little bit of function notation, can you see that f of 3 means replace 3 in place of x everywhere it occurs in the function? And similarly here. So you might need to rewind the presentation, have another look and check it out. Now what I want you to do when you've done a couple of problems is to go and look at the fully worked solutions. Now I've got those down the page there a bit. Instead of just the answers, I've actually put out the fully worked solutions provided by Hayes and Harris. So let's just go down there a bit so that you'll be able to fast forward when you've done a few. And there, I think, can we fit them on? Almost all of them. Yep. So I think that says only goes to part B. I know there's one down there as well. So here, we'll just, when you've done question 1A and B, you can come to this, scroll back and pick up the solutions. So I'll just pause it there, come down a bit to make sure all of 4 and 5 are on there as well. So you can play with this presentation, obviously, do your answers, get to a point where the solutions are all visible in the screen, mark your work, and then go back again, just toggle back, just like you would on YouTube, for example. So we'll go back actually to the problems here. That's where you want to go now. Okay, and you might pause the presentation and have a go. You know where to find the answers. Well, that's all there is in this first part, just to try and warm you up. But remember, what we're doing, this is an exciting subject. We're going to try and, even devise functions, make up functions, if you like, do modelling, model practical situations with mathematical graphs and functions so that we can use mathematics well to answer questions. Practical questions. So that's the fun of this subject. All right, so that's all from me at the moment. So it's cheers for now. Catch you in part 2 where we're going to do some modelling. Cheers.